Hello everyone, Dr. Hasbullah here, and in this video we are going to be looking at the integral form of fundamental laws. So basically in fluid mechanics, there are three basic laws that all fluids must follow. There are three laws, but before that we must know that these laws are expressed in terms of system. You may have heard this before, that we have two ways of describing fluids, whether through control system or whether through control volume. A system is basically a fixed collection of material particles. For example, if you have a fluid flowing through a pipe from left to right, and then you have this as your system, you have defined this as your system boundary at t equal to 0. And then a moment later at t equal to 1, then this system may have been transferred here and it may have changed the shape, but the number of particles that is inside the system remain the same, and this is what you call a system. A volume, however, is a region that is fixed in space. For example, if you have this junction like this, and you have a flow coming in from the left and it goes out to the right and upward, you can define a volume that is here. If you just want to study the junction, okay? So a volume is fixed in space, and this is called control volume. And the boundary that defines control volume is called control surface. Now, the reason why I need to introduce to you to system and control volume is that because the basic laws are expressed in terms of system. But as engineers, we usually look at a certain device and then we need to fix a control volume just to study that device. So later, when we have the equations in terms of system, we have to translate it into control volume so that we can use it. But before that, let's take a look at what are the basic laws. So the first law is called conservation of mass. The second law is called conservation of momentum. And the third law is called conservation of energy. Now let's take a look at what each of these means. Okay, first of all is conservation of mass. And for conservation of mass, the law states that the mass that is contained inside a system must remain constant. Okay, so mass inside a system remains constant. And how do we develop the integral equation to represent this conservation of mass law? Okay, so first of all, we know that mass is equal to rho times volume. But as the flow goes from point 1 to point 2, then the density could change. So conservation of mass says that mass inside a system remains constant. It means that mass does not change with time. So what we can write here is d over dt of the integration of rho times dv is equal to 0. And this is the integration of a system. And remember, rho times dv is actually mass. Right, and that is the equation for conservation of mass. And the second law is called conservation of momentum. And the law of conservation of momentum says that the rate of momentum change is equal to force acting on a system. So I think this is quite straightforward. We know that momentum is mass times velocity, but we also know that mass is equal to rho times v. But rho may change or may not change, so mass must be represented with the integration of rho times dv. So the change of momentum is d over dt integration over a system, and this is velocity times mass, rho dv, and this is equal to the summation of forces. And this is the equation for conservation of momentum. And finally, let's take a look at conservation of energy. And the law of conservation of energy says that the rate of heat that is transferred into a system minus the rate of work that the system is doing equal to the rate of change of energy. Okay, so that is pretty straightforward. So the rate of heat that goes into the system minus the rate of work that the system is doing equal to the rate where energy of the system is changing. And I think if we are to represent this rather mouthful definition into equation, it will look something like this. So the rate of heat, so this is Q dot, minus the rate of work, this is W dot, equal to the rate where energy of the system is changing. It means that d over dt, this is the rate where the energy is changing. So energy is mass times E, and as usual, mass is integration of rho dV. So this is E, this is integration over system, E times rho dV. Okay, and E here, small e, is the combination of kinetic energy plus potential energy plus internal energy per unit mass. So this is U. Okay, so that is your equation for conservation of energy. And also there is another term for conservation of energy. We also call this first law of thermodynamics. And another term for conservation of momentum is called the Newton's second law. Now that we know what are the laws, which are the conservation of mass, conservation of momentum, and conservation of energy. And as you may notice, everything that is described under basic laws is under the system. Okay, but as engineer, we are usually very interested in control volume. And if you notice, these are all the integration inside the system. Now we still need to use these three basic laws, but we need to transform these equations. So we need to transform this equation, conservation of energy, conservation of momentum, and conservation of mass. We need to transform this equation from a system to control volume so that we can use it in our calculation as engineer. But before we see the equation that can be used to transform system to control volume, let's see how we can organize this equation so that it can be represented into one simple equation. And we are going to do that by using a symbol to represent mass, momentum, and energy. And that symbol is N system. So basically, N system is the extensive properties of fluid, which include mass, momentum, and also energy. And we are going to use this N system by using a symbol eta times mass, which is rho dV. And of course, this is the integration of the whole system. So for example, if we want the N system to be mass, for example, so if N system is mass, then eta becomes 1, meaning that mass of the system is equal to integration of the system's rho dv. Okay, and if you remember that for a while, and is exactly equal to this, which is the mass. And we know that the change of mass inside the system remain constant. This equation can be represented as dn system over dt is equal to 0 for conservation of mass, so this becomes, because n system is equal to mass is equal to integration of rho dv, so this is volume, so it becomes d over dt, integration of a system, this is rho dv equal to 0. And this gives you back the equation for conservation of mass. Now let's say that n system is your momentum, then your eta becomes v. Okay, so now by using this equation, your momentum of the system becomes, let's take a look, so eta rho dv, so this becomes, when eta equal to v, so this is v rho dv, v rho dv. So remember, this is velocity and this is volume, and this is over a system. And conservation of momentum says that d n system over dt is equal to summation of forces. And this becomes d over dt, v rho dv of a system becomes summation of force. And this gives you back the equation for conservation of momentum. Right? And again, if n system is energy, then your eta becomes E. And by replacing eta equal to E in this equation again, you can develop the equation for conservation of energy. So now that we can generalize the system extensive properties, which is mass, momentum and energy, using n system, it is now the time to see the equation where you can transform system to control volume. And the equation is called Reynolds transport theorem. And Reynolds transport theorem looks something like this. This is dn system over dt equal to the integration of control volume. Remember, what is our control volume? And this is del over del t rho times eta dv plus the integration of control surface of eta times rho times n dot velocity times dA. And do you remember what is control surface? Control surface is simply the boundary for control volume. Okay, this is the control surface. Okay, now if you notice here, Reynolds transport theorem gives you the ability to convert system into control volume, isn't it? So now whatever laws that we have learned before, conservation of mass, momentum and energy, which is exclusive to system, we can also use that into control volume. And this is important because as an engineer, we are almost always interested in control volume. For example, if you want to study a turbine, okay, of course you're going to fix the control volume to the inlet and exit of the turbine. You are not going to follow a system that goes inside the turbine and study what happens to that system, and then it goes out and who knows where the system will go. Okay, but to know the operating condition of that turbine, we have to know the inlet and exit condition, and that is fixed in space, which means your turbine is a control volume, which is why Reynolds transport theorem is very important. Now let's go over a few terms that is inside this Reynolds transport theorem. First of all, you have dn system over dt. N system, you know before, this is the extensive properties of the system. This is mass, momentum and energy. And then you have del over del t times rho times eta You know very well what eta is. If eta equal to 1, that equals to mass. If eta equal to v, that is momentum. And if eta equal to E, that is energy. And then you have here dv. V is volume. And then you have the second eta, and then you have rho. You have n dot v here. This is the vector quantity, meaning that the velocity that goes out of the control surface must be perpendicular to the surface. And then times dA. dA is the area of the control surface. Now we can actually simplify this equation further, but remember that this depends on situation. For example, if you have steady flow means the flow does not change with time. So what happens is that this term can actually become 0. Okay, and let me back that up. So for steady control volume, then dn system over dt is equal to integration of control surface eta rho n dot v dA. Now this simplifies a lot, right? And let's say that the device looks something like this. Okay, it's got a box which maybe contains turbine or compressor or anything, and you have this inlet and you have this exit. So if you draw a control volume, it may look something like this. Okay, this might be your control volume. And what you have here is the velocity that goes in and the velocity that goes out. And if you notice, this velocity is already perpendicular to your control surface, and you have one inlet and one exit. Let's label this as 1 and let's label this as 2. Now, what happens to our equation here? So this becomes dn system over dt equal to, now you have one inlet and one exit, and this is the integration over control surface. And we have to be careful a little bit about this here, n dot v, meaning that if normal is in the same direction as velocity, then it's a positive value. If the direction of surface normal is opposite of v, then this value becomes negative. Now let's take a look at point 1 here. So n dot v, so v is going this direction, but normal is going out of the surface. This is your n, so this becomes negative v. Okay, but at your exit at point 2, normal is going out of the surface, so this is your normal. So n dot v becomes positive v. Okay, and what you have here is the integration of A2. This is the exit condition because A2 is positive. So now this is eta times rho times v dA, and this becomes v2. And let's label this properly. So this is eta 2 rho 2, and because v1 is negative, I'm going to write negative here. This integration of A1, this is eta 1 rho 1 v1 dA. Okay, and this is simplified enough actually, but we can actually simplify this even further if we assume that the flow is uniform. Just now we assume that the flow is steady, right? Right now, let's assume that the flow is uniform flow. So let me use purple this time. So for uniform flow, this equation simply becomes dn system over dt equal to eta 2 rho 2 v2 a2 minus eta 1 rho 1 v1 a1, right? And I think this is even simpler, and in many cases we can actually get away with assuming uniform flow. But of course, this must depend on case. So each case is different, but if you can assume that the case is steady and that the flow is uniform, you can simplify the Reynolds transfer theorem into this equation. So this equation is valid for uniform flow plus steady flow. Okay, so what happens if the flow is uniform but not steady, unsteady? Okay, and this equation becomes dn system over dt. Previously, we have removed this term, isn't it? But now, because the flow is not steady, we have to include this term, but now the flow is uniform. So these terms becomes the volume of the control volume times del rho eta over del t. del rho eta over del T, put this in bracket, and then we have this term, plus eta 2 rho 2 V2 A2 minus eta 1 rho 1 V1 A1. Okay, and let me color this in orange. And this is for uniform but unsteady flow. Okay, and I think that's it for now. After this, we are going to take a look at how to use, let's say, conservation of mass in this equation, for example. And then we're going to learn how to use conservation of momentum in this equation. But that is the topic for another video. For now, just make sure you understand what are the three fundamental laws that the fluid follows, and then take a look at the Reynolds transport theorem, the full equation, and see how you can simplify the equation for uniform and steady flow, and then uniform and unsteady flow. Okay everyone, that's all from me for now. I'll talk to you soon. Bye.